first is that a coin has a 50%, a 50% chance of tails or heads. Okay? We know, I discovered that, I recreate the central limit theorem with a coin, I remember, and I threw the coin 1,000 times, and I really discovered what it meant. It meant that if you throw it 1,000 times, the result of you have about 500 tails and about 500 tails, heads. Okay, but if you throw it like twice, the result can be yes, anybody. So throw it twice and it will. Okay. So yeah, he understood. He knew the work of Bernoulli. Okay, that the central limit theorem, and 100, roughly 100 samurai is a good base, and a good sample to so the central limit theorem works. So the idea is that if we start, if the chance is 50%, let's see, I will see one solution and the other I'll tell you tomorrow. Okay, Gauss solution of Gauss. The Gauss, when he went home, Gauss. Already Gauss, or the ancient writing is Gauss with a beta, which just means with 2 S. The idea is you have 50%, initial is 50, so according to the probability theory, alive with probability, okay, well, like this, is half. So 49 should be 44.5, even though it's impossible because half a samurai alive, just dead or alive, right? But that's the number. And then is 50% of that, which is 22.25. And according to the probabilities, and then the alive will be half, which is 11.125. And then you see they're similar, not the same. And then with 5.5, I'm too tired to do the operations with my hand, with my head, mental operation. So I'll do it with the calculator. So if you allow me, I'll read the messages later. Sorry about with the calculator, but it's 4.5, and then it's 0.65, 511, 1, I don't know, or 550, 060, I don't know. My head is like full of clouds at this time. Divided by 2 equal 5.5625. 5.5625, and then if I divide it by 2, the result is 2.78. Close, but they're not the same. 78125, and you divide it by 2, 1.391 to run it off. And then the last day, they should be alive like 0.695. So it's less than 1 samurai alive according to the probability. Okay. No. I jumped 1, right? So the first day was 89. Yeah, that's it. That's why it's so different. Sorry. I skipped 1 line. 49 divided by 2 is 44. I'll do it again. 44.5, which is similar, okay? And then divided by 2 is 22. 0.25, which is not that different, but it's different, definitely. Divided by 2, 11.125. Divided by 2 is 5, yeah, 4, 5, not that close. 56, roughly. Divided by 2, 2.78, 2, 3, yeah, almost 3, but and yeah, 1.39. That's the prediction. Yeah, now. So if you do a probability calculation, so every time you have a 50% of being alive, 50% of the previous one, right? We start with 89, 50%, that's the prediction. So Gauss was a prince of mathematicians, right? Because he did more than that, not only that. So with this, I saw that the captain had made this calculation. So that's the only way. But the margin is so thin, you know. The prediction is 1.39.1. Yeah, but it's a prediction, right? Prediction is 50%. So if I throw it twice, you know, like now I have to get the other one. Yes, the prediction in this case, but here, and then I have to get, yes, I did. 1, come on. No, yeah, again there. So it's a probability, not a certitude. But Gauss was very clever, and he had developed a system. So you say, oh, come on, if you plot it, come on, how to tell you now? If you plot the number of samurai alive with time, so day 1, see, this is not day 1, this is day 0, so mathematically it's more simple. 1, 2, 3, 4, 5, and 6. Because you know day 1 started with 0, like all the functions starting 0. So let me say this is 90, right? 90, 45, right? Roughly. Do 22.5, 22.5. So first day, I'm plotting this, the real values. 89 in the 0, okay. And then 49 will be roughly here. And then 18 will be around here. And then 7, and then 4, and then 2, and then 1. And he thought, come on, this sounds like the exponential decrease that we mentioned in a previous video. But how can I get the equation of this line? I can plot like this by hand, yeah, but how can I get